You will, if you've not already, and you've indicated earlier that you don't think you've done much work on these yet, but in your electronic principles, you will be looking at AC circuit. So this is an AC circuit, so a source of alternating current here. Good, okay. And have you applied it to inductors and resistors? Right, so when we do that, then you probably have talked about the fact that if I put a voltage across, so this is measuring the voltage against time. So that's a familiar AC trace. And you might remember that in an inductor is made up of a coil of, in theory, zero resistance material. So it's nice thick copper wire wrapped round some sort of core. And what happens when an alternating voltage goes across it, there is a back EMF induced that resists the flow of current. And the size of that resistance depends on the rate of change of the current. So the bigger the rate of change of voltage or current through the inductor, the bigger this resistance is, this impedance so-called. So in other words, if I have a flat DC supply connected to this circuit, apart from an initial surge or resistance when I turn the circuit on, the inductance will have no effect. We'll just have a resistive circuit. It only comes into play when we've got an AC supply across it, because the voltage is continually changing. And it turns out that if we look at the circuit, we can actually represent it in two dimensions. If I look at this real axis that we've been talking about to do with complex numbers, this x-axis, then as far as the resistance in the circuit is concerned, the voltage across the resistance exactly matches the current. As I increase the voltage across a resistor, the current goes up correspondingly. And so if I were to plot on an AC trace voltage and current, the voltage and the current would map each other exactly. They might not be exactly the same size, but it would map each other. There'd be no lag between the voltage and the current. As soon as I introduce an inductance, though, the voltage across an inductor is out of phase by 90 degrees with the voltage across the resistor. When the voltage across the inductor is a maximum here, we've actually got effectively the minimum rate of change. So the voltage across the inductor will at that point be 0. The voltage across the inductor will be maximum at maximum rate of change, which is when the voltage is 0. So it's out of phase by 90 degrees. And in fact, we can show it on a diagram like that as positive. So the voltage across the inductor goes up here. And now if I want to find the total voltage in this circuit, it will actually be this value. So if I've got the voltage across the resistance and the voltage across inductance, the overall voltage will be there. And it will be out of phase with the current. The current is here. Look, there's the current, I, and the voltage up here is out of phase with the current. So we say in this case, the current leads the voltage in an inductive circuit. And I think you can see that what we've been talking about before the break, complex numbers, lends itself directly to this situation, because we've got a vector situation. We've got a voltage at an angle theta with the current. And so we can say the voltage is in or out of phase with the current, and we can say by how much. And we can use complex numbers to do that. And that's what this is about. So let's look at an example of a voltage across an inductor and a resistance in series. So I've got a series resistor with an inductor. There's a symbol for an inductor across an AC supply. Let's say we've got a resistance of 5 ohms. And the inductor has an impedance, Z, of 10 ohms. In your electronic principles, you'll talk about how you can calculate that inductance from the reactance of the inductor and so on. There's a formula that allows you to do that. But at this point, I'm just going to tell you what the overall impedance of this thing. So you might have talked about the fact that in an AC circuit, we don't talk about resistance, we talk about impedance, Z. So the impedance of this inductor is 10 ohms. Let's put a supply voltage of 20 volts across this. So it's 20 volts AC. What I want to do is to calculate what the current is flowing in this circuit and the phase difference between the voltage and the current. So I'm going to calculate the current flowing and the phase difference between the voltage and the current. Something that anyone doing any AC theory calculations to do with electronics would want to do regularly, and we use complex numbers to do it. So, right, so calculate the current. Well, as in any circuit involving current, voltage and resistance, or impedance in the case of an AC circuit, Ohm's law. So Ohm's law tells us that the current flowing in this circuit equals the voltage, and in an AC circuit we tend to use the letter E to represent the voltage rather than V, divided by the impedance Z rather than R for resistance, but it's exactly the same formula. So I equals V over R, or I equals E over Z. E we know, E equals the voltage, which is 20 volts. AC. The problem is in the Z. Z is a complex number. It's a complex number. And it's got a real part and an imaginary part. The real part represents the resistance, so in this case that's 5 ohms, if I remember rightly. Yep. And the imaginary part represents the impedance of the inductor. So in the case of the inductor, this impedance, this imaginary part, is plus. So we got the real part plus this impedance due to the inductor. As we'll see when we look at an example for capacitor, it's negative. Because in the case of inductor, the current leads the voltage, so that makes it positive. In the case of an capacitor, it lags, so that makes it negative. So plus for inductance, minus for capacitance. So therefore, ZT, the total impedance, equals 5 ohms, which is the impedance of the resistor, plus, because it's an inductor, 10 ohms for the inductor, T, the total. And so we have a complex number. The imaginary part represents the impedance of the inductor, so that's 10 ohms, and the real part represents the resistance of the circuit, so that's 5 ohms. So we write ZT equals 5 plus 10J. It's a complex number. So now we have the current remember, from Ohm's law, equals E over Z, which equals now 20, because that's the voltage of the supply, divided by a complex number, 5 plus 10J. So we've got to do a complex division. The top number is a real number, so we can say effectively that the imaginary part of that is 0, but we've actually got one number divided by another number, and we've got to use complex number division to do it. The easiest way to do it, because we want our final answer to be in polar coordinates to give us the phase angle, is to convert to polar. So what we do is we convert each of these numbers to polar, and then use what we were doing before the break. When we divide the moduli and subtract the angles. Okay. The only thing to think about is this 20 volts. If we've got 20 volts and it's a real number, and there's no imaginary part associated with it, what angle does that have? 0, right. There's no angle. It's all along the real axis. So what we do is we say this equals 20 angle 0, or argument of 0, because it's got no imaginary part associated with it, divided by, and then we convert this to polar coordinates. So using the calculator, convert that to polar. 11.2 is the modulus, and 63.4 is the angle in degrees. And so now we use the rule to divide. We divide the moduli, so it's 20 divided by 11. So therefore the current equals 20 divided by 11, which is 11.2. Rounded 1.79. That's the size of the current. So what's the current flowing in the circuit? 1.79 amps. And the angle is, we've got to just do this subtraction, so nothing, 0 minus 63.4 is minus 63.4. Minus 63.4 degrees. So we can say that the current is 1.79 amps, and it lags by, and the voltage lags the current by 63.4 degrees. And the voltage, yeah, sorry. And the voltage lags the current by 63.4 degrees. Lags because it's minus. So in an example where we have a capacitor and a resistor in the circuit, the argument is exactly the same. The method is exactly the same, except for the fact that for a capacitance, the imaginary part is negative. And so we write down again that ZT, the total impedance, equals the resistance, which is the real part. So that's 6 ohms. But this time it's minus 12J. So we can write down, without further ado, what the total impedance of this circuit is. And then Ohm's law tells us that the current is voltage over resistance, or E over Z, which equals 20 over 6 minus 12J. And now we convert to polar, do the division, and that gives us a solution. So, yeah. So if you would like to just finish that problem off. So there we go. Convert, we get 1.49 amps, and the voltage leads the current by 63.4 degrees. So we've got instantly the size of the current in the AC circuit, and also the phase difference between the current and the voltage, just by using these laws of complex numbers. What do we do if we have this situation? I've got an inductor, and in a real inductance, you never have pure inductance. There's always going to be some resistance in the circuit. So actually, if I want to represent an inductor in a circuit, that would normally be represented by this. That together makes up an inductance. It's got an inductive part to it and a resistance part to it. So in any component, there'll be a resistance and an inductance in any inductor. So let's say I had 2 ohm inductance and a 5 ohm resistance. So it has, this particular component has an inductance of 2, an impedance of 2 ohms rather, and due to its inductance, and a resistive impedance of 5 ohms. And I connect that now in series with a capacitor which has a resistive component of 1 ohm, say, so 1 ohm and 4 ohms. And I put them in series. So that's 2 components put in series with a supply volts of 20 volts, say. How would I go about finding the current and voltage in a circuit like that? And what would I do about the fact that they're in series? Yeah, I'd add them together using complex addition, adding the real parts and the imaginary parts separately, remembering that the capacitive impedance is negative and the inductive impedance is positive. So the total impedance would be 5 plus 2j for the impedance, the inductor, and 1 minus 4j for the capacitor. And then I'd add them. And we know how to add. We just add real and imaginary parts separately. And then the problem would be exactly the same from then on to find the total. Yeah. What about, yes, but what about this? What about putting a 20 volt supply across this? How are they connected? How are they connected? In parallel. What do you do to find the total impedance of 2 things in parallel? I'm waiting for, pardon? No? No? What's the rule for resistors in parallel? For resistors in parallel, 2 resistors in parallel, come on, you do know this, it's product over sum, isn't it? Yeah. So if I had 2 impedances in parallel, I would have to work out what the 2 multiplied together were, remembering the rules for complex numbers, and then divide that by the 2 added together. So I'd have to add them up, and then I'd have to use complex division to find the total impedance. And then I would use Ohm's law. Which sort of question do you think you've got in the assignment? As a guess. Which one's the most difficult? So which one do you think I've given you?